I'm Madalena, a software developer at Progeneric Systems. Our Parallel Template Library, or PTL, contains many powerful and easy-to-use parallel functions that take advantage of multi-core processors. In this video, we will demonstrate the performance and scalability of PTL by using it to solve the Pentomino puzzle. We'll run this demo on a system with two Intel Xeon 6-core processors for a total of 12 physical cores. With hyperthreading, we have a total of 24 logical cores. To solve the Pentomino puzzle, you must fill a rectangular board with all of the Pentomino shapes without any overlap or gaps. Each Pentomino shape has several possible orientations, with a maximum of 8 possible orientations. There are over 67 million possible combinations of the shapes. Let's see a few of the combinations now. We could create an array to hold all of the possible combinations, but it would require several gigabytes of memory. Instead, we implemented an iterator that uses lazy initialization. It generates each combination when we need it. Iterating through all of the combinations is faster than storing them all in memory, which we will show now by running all 67 million combinations without displaying them on the screen. It takes a little over 1 second. For each combination, we use the branch and bound algorithm to place each shape on the current board until we either find a solution or we fail, as shown in the place shape method from a sample solution. The key functions in the place shape while loop are isSafe, insert shape, and remove shape, and we'll show their implementations later. This algorithm can take thousands of trials per combination, which can result in tens of billions of trials. Here, you can see the sample solution in action only for the last 24 trials before it finds a solution. The branch and bound algorithm is very useful in many applications, such as nonlinear programming, the traveling salesman problem, and false noise analysis. We will demonstrate both sequential and parallel solutions to the Pentomino puzzle using this approach. First, let's run a sequential solution for 3 million combinations. While it's running, let's take a look at the code. Here we can see the isSafe, insert shape, and remove shape methods that we mentioned earlier. This code is highly optimized. We determined up front all valid positions on the board for each shape and stored them in a 2D array of Boolean values. If we determine these valid positions at runtime, it would take tens of hours to finish a run. We'll fast forward to when the sequential solution finished. As you can see, it processed around 11,500 combinations per second, and it found all 423 solutions in 4 minutes. Now, let's run a sequential solution using PTL. Let's inspect the new sequential code using the PTL BitSet Classes. Now, the isSafe, insert shape, and remove shape methods, which are executed tens of billions of times, are much smaller and much faster using PTL. We'll fast forward again to when the PTL sequential solution finished. The PTL solution processed around 28,000 combinations per second. It found all 423 solutions in 1 minute and 38 seconds, which is 2.4 times faster than the previous sequential solution. Finally, we'll show a parallel solution using PTL. On top, the code for the sequential PTL solution is shown. For the PTL parallel solution, this sequential code is simply moved into the parallel for each method of the PTL algo-based class, using a feature called a lambda operator. All of the partitioning, load balancing, and allocating threads for execution is done internally by the library. Now let's run the parallel solution. PTL parallel solution can process around 424,800 combinations per second. It found all 423 solutions in 7 seconds, which is 12.3 times faster than the PTL sequential solution. Let's execute the parallel solution again for 10 million combinations and track the performance in Windows Task Manager. In the Task Manager, you can clearly see that all 24 cores are very busy and working simultaneously to solve the Pentomino puzzle. To conclude, we'll leave you with a chart comparing the results of all 3 solutions for 10 million combinations. This chart shows the 2.4 times performance improvement of the PTL sequential solution using the PTL BitSet Classes. It also shows a tremendous 13.3 times improvement of the PTL parallel solution using the PTL parallel for each method. You can read more about the benefits and functionality of PTL and also view its complete documentation under the Products section of our website. Thank you for watching this demo.